Yeah, do that from this.
Yeah.
Yeah.
All right, it's 5:30. Let's go ahead and get started. All right, good evening, everyone. How's everyone doing today?
Pretty good.
Good to hear. All right, so we're end of second week, so we're really getting into the swing of things. Plan for today is just to continue on with Truss stuff, and so I think we almost had derived the element stiffness matrix for a 1D truss, and so we'll finish that up. We'll do an example there, and then we'll move on to kind of the bulk of what I had planned for today, which is 2D trusses, and so. I think up until this point, the class, started fairly slow. We're kind of getting into the whole finite element process, starting with 1D problems. 1D problems are not the most exciting, but I think with 2D problems, things will kind of pick up a little bit. And yeah. All right, and so I think that's about it. I don't think that besides homework 1 being out, I don't think I have any more announcements. Are there any questions I can answer before we get started? Okay. All right, so let's go ahead and pick up where we left off. All right, so I'm just going to scroll up a little bit just so you can kind of see where we were. Okay. So we're looking at a truss element, right? And so trusses are basically structural elements that primarily support tension and compression. Okay. So basically, any kind of deformation or any kind of loading in the same direction as the element itself. Okay. So to derive the element stiffness matrix for a truss element, we subjected it to a tensile force, just like we did with our spring, okay? And we utilized the equations for the stress-strain relationship in the truss in order to obtain the following equation, right? So we said that the tension in the truss is equal to, or the amount of tensile force that we're applying on the truss is equal to the product of the cross-sectional area, the Young's modulus E, and divided by the length L, multiplied by the difference in displacement of the two endpoints, D2 minus D1, okay? All right, and so the last thought that I left you with on Tuesday was the fact that, this equation here looks very similar to our spring equation, right? And so if you think back, to last week when we derived the equation for a spring, right? We basically said the tensile force in a spring under the exact same conditions was equal to K times D2 minus D1, okay? So that looks a heck of a lot like what we have here, but obviously instead of the spring constant, we have this quantity instead, which is A times E divided by L, right? So that quantity there, we basically call the effective spring constant, okay? But since the governing equation is essentially the same as a spring, then it makes a lot of sense that our element stiffness matrix will look the same as a spring as well, okay? So let's start with that. Okay. All right, so the element stiffness matrix for a truss is a 2 by 2 matrix, okay? So we have F1, F2, okay? So that represents the nodal forces at the ends of the truss, okay? Is equal to, I'm gonna factor out the AE over L just so I'm not writing it 4 different times. So we have AE divided by L multiplied by 1 minus 1 minus 1, 1, D1, D2. Basically the exact same form as our spring element stiffness matrix, but of course K is replaced by AE over L. All right, so we should feel very comfortable working with trusses because they behave exactly the same as springs. Okay. All right, so let's go ahead and jump into an example then. Let's see how this is used. Okay. And of course, through this example here, you'll be able to see the whole finite element process again. So hopefully that'll be kind of helpful for that. Okay. All right, so let's consider this assembly with 3 truss bars. All right, so just to keep things simple, we'll kind of link them all kind of in series. Right, so we have 3 bars connected to each other like that. Okay. We'll call the first one element A, second one element B, third one element C. Okay. We'll say the length of each bar is the same. We'll say they'll have a length of 30 inches. Okay. All right. And then for the other material properties, elements A and B are going to be identical. So elements A and B are going to have a Young's modulus, E, of 30 times 10 to the 6 psi. They're going to have a cross-sectional area of 1 inch square. Okay. Element C is going to be different. Okay, it's going to be made of a different material and have a different thickness. Okay, so element C here is going to have a Young's modulus of 15 times 10 to the 6 psi, and have a cross-sectional area of 4 inch square. Okay. All right. Let's go ahead and label all the nodes. And so we have node 1, node 2, node 3, node 4. Okay. And so just like we typically do in these finite element problems, we want to find the position or the displacement of all of the nodes in our system. Oh, I forgot the force, right? So actually, in this current state, all the displacements will be 0 because we're not applying any force. So we do need to apply a force. Okay. So let's say we're going to apply a force at node 2, and this force is going to be equal to 3,000 pounds. Okay. All right, but all other nodes are going to have no forces, and obviously node 1 and node 4 are going to be fixed to the wall. Okay. All right, so that's our setup, and so we're going to go through the exact same finite element process. The only thing that's going to change now is that we have truss elements instead of springs, but you'll see it's the exact same process from there. Okay. Any questions on just the setup for this problem? Okay, all right, so let's go ahead and start. So we're going to follow through with the same finite element process that we did in the last example. Okay, so step 1 always is going to be to compute the element stiffness matrices for all the elements. Okay. All right, so let's start with element A, right? So we know that the element stiffness matrix for element A is going to be F1, F2 is equal to AE over L times 1 minus 1 minus 1, 1. Okay. D1, D2. Okay. All right, so of course, we're given values for all of these variables. Let's go ahead and plug them in. Okay. So we know A for element A is 1 inch square. Okay. E is 30 times 10 to the 6th psi, and L is 30 inches. Okay. Okay. So we plug all these in. We get 1 inch square multiplied by 30 times 10 to the 6 pounds per square inch. Okay. All divided by 30 inches. And what we get is 10 to the 6 pound per inch. All right, so we can go ahead and plug that in. And so we plug that in. I'm going to go ahead and factor that through the entire matrix. And so this is going to be 10 to the 6 minus 10 to the 6 minus 10 to the 6, 10 to the 6, multiplied by D1, D2, F1, F2. All right. Now, of course, there's one extra step here relative to the spring. So we have to compute that AE over L. But that's usually just a simple thing you can punch into your calculator. Okay. All right, so let's do the same thing for element B. So we're in luck with element B because element B, at least in terms of its properties, is completely identical to element A. Okay. The only thing that's different about element B is the nodes that it's connected to. So if we go back to our figure here, we can see that element B is connected to nodes 2 and 3. So let's go ahead and reflect that in our element stiffness matrix. Okay. So we have F2, F3 is equal to 10 to the 6 minus 10 to the 6 minus 10 to the 6, 10 to the 6, multiplied by D2, D3. So I see this happen a lot, especially for a lot of people doing these kinds of problems the first time. If you see two elements that have the same properties, yes, they are going to have the same coefficients within the element stiffness matrix. And so you see that here, both element A and element B have 10 to the 6th inside their matrix. Okay, but what's not the same is that two different elements are going to be connected to different nodes. Okay. And so even if you have elements that have identical same properties, I still want you to write out the element stiffness matrix for every single element because they're all going to have different nodes. Okay. Because what tends to happen sometimes is that, if you kind of skip work, you see, you have four elements, they all have the same properties. And so you just write it once. Then when you go to assemble, even in your head, if you think like, all right, I'm going to put these in the right places, if you don't write it down, it's very easy to kind of miss something or kind of shift things over one. And then kind of chaos ensues from there. So, even if two elements have the same property, I still want you guys to write out the element stiffness matrix so that you can be really explicit in terms of, the number or the nodes that it's connected to. Okay, at least for the first two assignments, just so you kind of get used to these type of calculations. Okay. Okay, now we have element C. So element C does not have the same properties. So let's go ahead and compute that. Right. So let's go ahead and compute AE over L. So for element C, the cross-sectional area is 4 inch square. Okay. The Young's modulus for element C is 15 times 10 to the 6 psi. Okay. And the length is 30 inches. Okay. All right, so we do this arithmetic, we get 4 times 15 times 10 to the 6 up top, so that's 60 times 10 to the 6. We divide that by 30, we end up with 2 times 10 to the 6 pound per inch for the effective spring constant for element B. Okay. All right, so let's go ahead and plug this in. Noting the fact that element C here is connected to nodes 3 and 4, so this is F3, F4, okay, is equal to 2 times 10 to the 6 minus 2 times 10 to the 6 minus 2 times 10 to the 6, 2 times 10 to the 6, D3, D4. All right, so that's all three of our element stiffness matrices right there. Any questions on how we got these matrices here? Okay. All right. So now that we're done with the element stiffness matrices, let's go ahead and assemble. So let's go ahead and assemble this all into a single linear system so that we can solve. Okay. We have four nodes here. So nodes 1, 2, 3, and 4. And so we need our global linear system to have 4 rows and 4 columns. Okay. We have F1, F2, F3, F4 is equal to. We have our matrix here, D1, D2, D3, D4, D1, D2, D3, D4. Okay. All right, so just like we did in the previous example, let's go ahead and make note of the nodes that these elements are connected to, and then partition out the appropriate areas within the global linear system. Okay. So element A we know is connected to nodes 1 and 2. Okay. So nodes 1 and 2, that's going to be the first 2 rows, first 2 columns, basically where they intersect. Okay. Let's go ahead and write the values in here. So that's 10 to the 6th, minus 10 to the 6th, minus 10 to the 6th, and then 10 to the 6th. Okay. Okay. Next, we have element B. Element B is nodes 2 and 3. Okay. All right, so let's go ahead and partition that area out. Okay. And just like before, let's go ahead and insert the value. So that's going to be a plus 10 to the 6 because that we have an overlapping part there. Minus 10 to the 6, minus 10 to the 6, 10 to the 6. Okay. All right, and then finally we have element C. Element C we know is connected to nodes 2 and 3. Or 3 and 4, excuse me. All right, and so let's go ahead and partition that area once again. Okay. Here we have a pretty straightforward case. It's all the elements are in a row. Okay. So let's go ahead and add in our contributions from element C. So we have a plus 2 times 10 to the 6, minus 2 times 10 to the 6, minus 2 times 10 to the 6, and then 2 times 10 to the 6. Okay. Everywhere else that we have not circled is going to get a 0. Okay. So we have 0, 0, 0, 0, 0, 0. All right, and so of course, wherever you have kind of the overlapping boxes, you can go ahead and add those together to simplify. And so in the first one, we have the 10 to the 6 plus 10 to the 6. That's going to be a 2 times 10 to the 6. And then the bottom one, we have the 10 to the 6 plus 2 times 10 to the 6, which is going to be 3 times 10 to the 6. Okay. All right. Any questions so far on this? Okay, good. All right, next let's go ahead and apply our boundary conditions. All right, so we have 3 boundary conditions we need to apply here. We have 2 fixed constraints and 1 force. Okay. All right, so the first one is we have a fixed constraint. Or in other words, we have a Dirichlet boundary condition on node 1. Okay. All right, and so we know what to do in these situations. So for node 1, that means we're going to replace the first row of the matrix with 1, 0, 0, 0, and then replace F1 with 0. All right, so let's go ahead and do that while I have kind of both in the same image here. Okay. So the first row, instead of 10 to the 6 minus 10 to the 6, 0, 0, we're going to go ahead and erase these. Okay. All right, so first thing we're going to do, let me go ahead and change colors to green. Okay. Okay, so we're going to replace the first row. So remember, we're going to put a 1 in the diagonal and zeros everywhere else. Okay. And then we're going to need to replace the F1 with 0. Right, so that's indicating the fact that D1 is going to be equal to 0 because it's attached to the wall. It's a fixed constraint. Okay. All right, next we have a fixed constraint on node 4. Right, and so we're going to do the exact same thing on node 4. But this one's going to be a little bit different because we've always done fixed constraints on the first row. Okay. I think someone made an observation of this in the last class where if you're applying a fixed constraint on a row other than the first one, you have to move the location of the 1, right? So instead of being 1, 0, 0, 0, since we're on the 4th row, we're going to put the 1 in the last column. Okay. Right, so let me kind of show you what that looks like. All right, so for fixed constraint on node 4, in the matrix, we're going to have 0, 0, 0, 1. Okay. Because remember, the entry that we're setting equal to 0 in this case is D4. And so, the column that corresponds to D4 is the last one. Okay. And then on the left-hand side, we're going to put a 0, at that part. Okay. Okay, so that's 2 boundary conditions down. the last one that we need is we need our applied force on node 2. Okay. So here we have a simple, very simple Neumann boundary condition. We have a force that's being applied in the positive x direction. And so all we have to do to apply this is we're going to replace F2 with 3000. Okay. All right, so remember for Neumann boundary conditions, for force boundary conditions, we don't make any changes to the matrix. We only add those entries just to the forcing vector. Okay. All right, so we do that. Our F2 here is going to change to 3000. Okay. All right. And then finally, technically, we have a fourth boundary condition for node 3. Our boundary condition on node 3 is there's no boundary condition applied on node 3. And so we're just going to put a 0 for F3. Okay. All right. And so actually, let me go ahead and change these. And so this overlapping entry here, this is going to be 2 times 10 to the 6 because we have 2 10 to the 6s added to each other. And then on the bottom one, we have 3 times 10 to the 6. All right, so we are all good to go. So we have our linear system, we have our boundary conditions applied, we have everything we need to solve, okay? So I'm not going to put this into MATLAB again, but just know that, you can use MATLAB to solve this because it's a 4x4 system, okay? Technically, I guess it's a 2x2 system because your first and fourth rows are knocked out, but, regardless, it's not the easiest to solve with these numbers. Okay? And so step 4, solve in MATLAB. Okay. And so, refer to last lecture in terms of how you put a matrix like this into MATLAB. Okay. And so if you do that, you get D1 is equal to 0 inches. Okay. D2 is 0.0018 inches. D3 is equal to 0.0006 inches. And D4 is 0 inches. All right, any questions on that? This example here?
Dr. Tran, how?
All right, so that's it for 1D problems. And so, pretty straightforward. So basically the same as springs. Now we're going to get into 2D problems. Okay.
Hey, Professor.
Yep, what's up?
I think someone had a question on the chat.
Oh,
Or
thank you. All right. Question. So what would you put in your stiffness matrix if there's a mixture of truss and springs? That's a great question. And in fact, probably you're looking at the homework because there's a problem like that. So if you have a mixture of truss and springs, and actually it's going to be very common for us to have a mixture of different types of elements, especially once we get to beams and frames. You can handle it in the exact same way. And so, the only thing that's going to be different is step 1, which is compute the element stiffness matrices, right? So if you have a spring element, you're going to compute the element stiffness matrix using its spring constant. If you have a truss, you're going to use it. You're going to compute the element stiffness matrix using the cross-sectional area, the Young's modulus, and the length. Okay. And so ideally, in most problems, you're going to have numerical values for all of these quantities, right? And so, once you insert the numerical values and you just have the matrices, from there, we've kind of, forgotten, or it doesn't really matter what our element types are. They're just numbers and matrices, and they're attached to nodes at that point. So, once you get to the assembly step, and if you have springs, you just plug in whatever value that you get from the spring constant, and you just make sure you plug it into the appropriate place here. Yeah, good question. Yeah.
Last lecture, you mentioned that you like to keep everything in variable form and then compute.
You can do that too.
Given that it would get really ugly when we have that high, truss spring. Would you recommend we leave everything variable until the end, or should we compute first?
It's personal preference.
Okay.
But yeah, it does get very messy, especially when we get to beams. Beams are going to be very, very messy. And so, in those situations, it probably is beneficial to compute all the numbers first. But sometimes the numbers could also be very messy as well. So, you can't really get around the messiness at some point here, especially once we start to get into 2D problems. And so it's kind of just like pick your poison. Do you want to write a bunch of variables, or do you want to write an irrational number with like 17 places after the decimal? So, yeah. All right, any other questions on this? Okay. All right, so let's get to 2D problems. All right. All right, so far, we've introduced the concept of finite element problems, that we've done them in 1D, okay? Of course, we don't live in a one-dimensional world. It might be simpler that way, but, we live in a three-dimensional world. 3D is, typically, when you take a science or engineering class, a lot of times the theory is developed in 1D, and then the professor kind of waves their hand and be like, oh, it's kind of the same in 2D. We're not going to go there. It absolutely is not the same in 2D and 3D. It's kind of a lot more complicated when you have more dimensions. And you'll see that very quickly once we get here, okay? But, because FEA, you can't really have FEA in just 1D and call it a day. We're going to go through some of the details that are required to take a problem and take it to the second dimension, okay? Okay. So the main difficulty that we're going to have in 2D, especially for truss and spring problems, is the fact that, the truss and springs, if you're having truss and spring elements pointing in different directions, those deformations are not going to align with each other. Okay? Okay. All right, so let's draw kind of a simple example here. So let's say that we have, a truss element right here. It's facing some kind of diagonal direction. And then let's say it's supported by another truss element that's like this, okay? Right, so our assumption up until this point for both truss and spring elements is that they are only capable of extension and compression. Okay? And so let's say for the first element here, it's only going to be able to deform in that direction. Okay. And then for the second element is only able to deform in this direction. Okay. All right. So for all the 1D problems so far, if you looked at all of our 1D problems, we've arranged the elements in a way such that their axes are always aligned with each other. And so, if one side is extending and compressing in one direction, that's the same direction as another one, okay? The fact that we have elements now that are facing different directions is going to be actually quite complicated, okay? Because our derivation of the element stiffness matrix up until this point kind of assumes a uniform coordinate system. Okay? another way that we can say it is that our coordinate system, or at least our element stiffness matrix, is defined relative to a local coordinate system. Okay, so we can write out the element stiffness matrices of both of these elements here. Okay, and so if we call this left element here element A, right? The element stiffness matrix for this is going to be F1, F2 is equal to AE over L, 1 minus 1 minus 1, 1, D1, D2. Okay. But that is defined assuming the fact that F1, F2, D1, D2 are pointing in the directions of the purple arrows. Okay. Okay. Now we can do the same thing for element B, the pink element. Okay. Right, so we can define its element stiffness matrix in the same way. But again, that's going to make the assumption that that element stiffness matrix, the deformations are in the directions of the pink arrows. Okay. And so, that's all that is fine, right? And so every element can have its own element stiffness matrix. The problem is when we go to assemble, right? So one thing that's kind of implicit to our assembly step is that, when we assemble different element stiffness matrices into the same linear system, we're kind of assuming that everyone in that assembled system is using the same coordinate system. Because then it wouldn't really make any sense because the D1 or the D2 of one element and the D2 of another element, those have to be facing in the same direction. Okay. And so in order to equate this, or in order to kind of fix this issue, we're going to need to perform a change of coordinate systems in order to change every element essentially, or not change the element is kind of fixed in space. Basically, we need to redefine the element stiffness matrices so that they're redefined as some universal, or I call it stationary coordinate system. And so for the next, 15, 20 minutes, we're going to be working on a change of coordinates, okay? So a little bit of geometry, well, actually a lot of geometry, and then that geometry is going to factor into our elements. Okay. All right, any questions on this so far? Okay. All right, good. So let's go ahead and see how we do this. So let's talk about change of coordinates for a little bit. All right, so change of coordinates, when you mention that in any kind of math or physical context, it can mean a lot of different things. But for our purposes, we're only going to be doing a simple rotation of the coordinate system. Okay. Okay. All right, so let me kind of draw two coordinate systems here for you. Okay, so on the one hand, we'll have kind of a very standard XY where X is horizontal and Y is vertical. Okay, let's call this our stationary coordinate system. Okay. So ultimately, we want to transform the elements' stiffness matrices to be relative to this coordinate system. Okay, because this is the one that we kind of generally we generally like to use because it's, you know, X is horizontal, Y is vertical. That's kind of what we've been drilled into ourselves, you know, at all levels of math. Okay. On the other hand, you know, you may have another coordinate system that's aligned with the element. Okay. So let's say that we have a truss element that's kind of rotated up like this. Okay. Right. So let's define a coordinate system relative to that element. Okay. So here we'll call this the local coordinate system. And the local system is, remember, aligned to a specific element. Okay. All right. So one thing that's going to be important so that we can relate the two coordinate systems, right? Since we are just doing a simple rotation, right? One way that we can define the local coordinate system relative to the stationary one is by some kind of rotation angle. Okay. So this angle here, theta, this right here is our the amount that we're rotating in order to get into our local coordinate system. Okay. Oh, one thing I forgot, I didn't label these axes, and so the x-axis for our local system, we'll call that x hat, and the y-coordinate system, we'll call that y hat. Okay, so we're going to give hats to denote that that's in the local coordinates. Okay. Okay, good. All right, so next thing I'm going to do, so now that we have our two coordinate systems, is I'm going to draw the same vector in both systems here. Okay, so I'm going to draw a vector that goes like this. So we'll call this u vector. Okay. Okay. And then we're going to draw the same vector over here. Okay. It's not going to look the same because I kind of am tricking myself just because I'm looking at different coordinate systems. But imagine these two vectors are exactly the same. Okay. I think that's pretty close. Okay. So u vector in the left on the left-hand side, u vector on the right-hand side, they are the exact same vector. Okay. Now, the way that we describe this vector is going to be different in the two coordinate systems because remember, the way that you define a vector or the way that you describe a vector is always relative to its, you know, the coordinate system, right? Okay. All right, so let's think about how we describe the u vector in the stationary coordinate system, right? So if we give it kind of the typical kind of two component description, right? The x component of u vector, we'll call that ux, okay? And the y component, we'll call that uy, okay? And then we can do the same thing in the local coordinate system. Okay? So in the local coordinate system, we can define the x coordinate as ux hat, and then in the y direction, we can define as uy hat. Okay? Same vector, we're just, describing it differently. It's like, you're looking at the same person, but you're looking at them from the front versus the back. Same person, it's just that, you describe it differently because your perspective is different, okay? Now, let's take advantage of this fact, right? So taking advantage of the fact that we have the same vector, we can kind of equate two quantities, or we can equate the two descriptions to each other in the following way, okay? So on the one hand, we have the description of the vector in the stationary coordinates, so that's ux multiplied by I plus uy multiplied by j, okay? Where I and j, those are unit vectors in the stationary x direction and the stationary y direction. Okay. So this is going to be equal to ux hat I hat plus uy hat j hat, where I hat and j hat, these are the unit vectors in the local coordinate axis directions. Okay. All right, but since this is the same vector, these two descriptions should be the same, okay? All right. Now, unfortunately, this description or this equation that we have here is true, right? It makes sense because u is the same vector, but it's not super useful to us right now, okay? And so the next thing we're gonna do is we're gonna go through a couple exercises to kind of replace some terms in this equation to get something that's actually more useful to us, okay? All right, before we do that, are there any questions on just anything that we covered up to this point? Okay, all right, so let's go ahead and work on this expression here, okay? Okay. So the way that we're going to do this is that, we're going to draw out each of the unit vectors, and we're going to define each of those unit vectors relative to the coordinate axes in the opposite system, okay? Okay. So in other words, let's draw not I hat, let's draw I. Okay. And let's define I relative to the coordinates in the local coordinate system. Okay. All right, so the I vector is the unit vector in the stationary x direction. So it's just going to be a horizontal vector here, okay? Let me give it a little bit more space. Okay, so this is I, right? Is a unit vector, so we know that the length of this vector is just 1, okay? Now let's define the components of I in the local coordinate system. And so the way we're going to do that is that, we're going to start from the origin here, okay? And we're going to draw a vector in the x hat direction. Okay. So we'll call this vector a hat. Okay. And then to complete our triangle, we're going to draw a vector in the y hat direction, okay, which in this case is going to be the negative y hat direction. Okay. So a hat is a vector in x hat direction. Okay. Remember, x hat is the x direction in the local coordinate system. Okay. And the b hat vector b hat is a vector in the y hat direction, or in this case, the negative y hat direction. Okay. Now we do know one extra piece of information here, just because we know how much the local coordinate system is rotated relative to the original one. And so we know that the angle of that triangle there is going to be theta, theta being our rotation angle. Okay. Okay. I know it's kind of hard to visualize, I know, but I want you guys to always refer back to this kind of figure here, right? And so, think about the direction of the x hat direction and the y hat direction, right? All we're doing is we're taking unit vectors in the x direction and eventually the y direction and defining those, within the directions of our local coordinate systems. Okay. Okay. So that's kind of how we got that triangle. Okay. All right. So now what we're going to do is we're going to use trigonometry, and we're going to use the fact that we know the hypotenuse of this triangle, because the hypotenuse of this triangle is just going to be 1, because remember I is a unit vector. Okay. We're going to use that to relate A and B back to I. Okay. Okay. So first, let's do A. Okay. Right. So let's use trigonometry to compute the length of A. Right. So A is this edge here that's kind of adjacent to that angle there, right? And so if you go back to, trigonometry, you go back to our good old SOHCAHTOA, right? And so, for the adjacent edge, we need to use cosine. Okay. Okay. And we're going to take cosine, we're going to multiply that by the magnitude of the hypothesis, or the length of the hypotenuse, excuse me. So the length of that A is going to be equal to the length I multiplied by cosine of theta. Okay. But we know the length of I is just 1. Right. So in other words, we know the length of A hat. A hat is simply just going to be cosine of theta. Okay. Okay, we can do the same thing for B hat here. So B hat, the length, is going to be equal to sine theta, right? Because B hat is on the opposite side from the angle, so that's the SO of SOHCAHTOA. Okay. Multiplied by I, which we know the length of I here is just 1. And so this tells us the length of B hat is just sine theta. Okay. All right, so now what can we do with this information? Okay. So with this information here, we can basically define the I vector relative to the components in the local coordinate system. Okay. Basically, we're kind of doing the same thing we did with our U vector, where we're taking our vector and we're defining it in the other coordinate system. It's just that we're doing it just for the unit vector in our stationary system. Okay. Okay, so what this looks like is I is essentially equal to cosine theta. Okay. So cosine theta is going to be the component in the I hat direction. Okay. Minus sine theta j hat. So I have the minus sign for j hat because if you look at the direction of the arrows, right? So in order to go from the end of the A hat vector to the B hat, we have to go kind of down. And so that's kind of that's technically the negative y hat direction. Okay. All right. So a lot of trigonometry, a lot of geometry there. So any questions on this part here? Okay, good. So let's do the same thing, except instead of the I vector, let's do it for j, okay? And so essentially what we're going to do is we're going to define basically each of the unit vectors in the stationary coordinate system in terms of the local coordinates, okay? And where we're going with this is if you go back to this kind of expression that we have for a generic vector, right? Essentially what we want to do is we want to plug in for I and j here, okay? Because if we can define I and j in terms of I hat and j hat, then we can plug that in and we can actually get an expression that we can actually use to relate the two systems. Okay? So we want to replace these with expressions. All right, so that's kind of our strategy, and that's kind of why we did that the whole triangle down there, right? But of course, we have one more triangle to draw because we have to do the same thing with j. Okay. All right, so let's do the same thing with j. Okay. So j is a vector that goes straight up, right? Right. And then so to define this in terms of the x hat and y hat directions, we have a b vector here, b hat, and just to differentiate, we'll call it b2 hat. Okay. And then we have a2 hat. Okay. Right. So the angle between b2 and a2 hat is going to be a right angle, and then our rotation angle is going to be this one here. Okay. All right, so let's do the same thing we did with the previous triangle. So let's go ahead and define, j in terms of the directions a2 and b2. Okay, but first we need to find the actual lengths of b2 and a2. Okay, so a2 hat, that's equal to, that's the edge that's opposite to the angle. So that's going to be sine theta, length of j. Okay, we know length of j is 1. And same thing for b2 hat, right? b2 hat is the adjacent edge to the angle. So this is going to be cosine theta times j, okay, which is equal to 1. Okay, so we put that those two pieces of information together. We get j is equal to sine theta times I hat plus cosine theta j hat. All right, good. So now that we have everything here, we can go ahead and plug both of these expressions back into our vector equivalence equation here. Okay. So let's go ahead and do that. Okay, so on the left-hand side of that expression, so we have ux times I plus uy times j is equal to ux hat, I hat plus uy hat, j hat. Okay, so if we're going to plug in for I and j using these expressions, let's go ahead and do that. All right, so we plug in for I first, so that's ux times cosine theta I hat minus sine theta j hat, okay, plus uy. We plug in for j. This is sine theta I hat plus cosine theta j hat, okay. This is equal to ux hat I hat plus uy hat j hat. Okay. All right. Let's take the left-hand side of this expression here and let's group like terms. So right now they're grouped by ux and uy, but let's group them by I hat and j hat instead. And so we do that, we get ux cosine theta plus uy sine theta I hat plus minus ux sine theta plus uy cosine theta j hat is equal to ux hat I hat plus uy hat j hat. Okay. All right, we're almost there, I promise. Okay. I know. I think the first time I learned this, I think the professor was like, "Oh, it's just geometry. It's easy." I was like, "Oh, geometry's kind of hard sometimes." So, especially when there's just kind of a lot of stuff going on. But yeah, we're almost there. All right. So in this form right here, we basically have two equations because in order for this equality to hold, right? Right, because we're saying that the left-hand side here is equal to the right-hand side. And so in order for this to hold, all of the I hat terms, so everything that's here, has to equal to the I hat terms on the left-hand side, okay? And then by that same token, all of the j hat terms, everything that's multiplied by j hat, has to equal to the j hat terms on the right-hand side as well, okay? So we can form two equations for these, okay? And just like we always like to do in this class, let's put these in matrix form. Okay. All right, so if we do that, we get the following. We have cosine theta, sine theta, minus sine theta, cosine theta. Okay. And this is multiplied by ux, uy. And this is equal to ux hat, uy hat. All right. So what we've derived here is we've basically derived a way for us to transform coordinates in one coordinate system to the other. Okay. So we call this matrix here, we call this the transformation matrix to go from the stationary coordinate system to the local coordinate system. Okay. All right. Any questions on this? Okay, good. All right. So how are we going to use this, right? So we've taken quite a detour. So, from this finite element class, we've only kind of done one finite element problem today, right? So ultimately, we want to use this transformation matrix to transform our truss element stiffness matrix. Okay. Okay. And so our truss element stiffness matrix for, let's say, a generic truss here. Okay. Our element stiffness matrix is going to be F1 hat, F2 hat is equal to AE over L times 1 minus 1 minus 1, 1, D1 hat, D2 hat, right? So remember, that element stiffness matrix that we've been working with is defined to a coordinate system local to the element, okay? But, like we mentioned earlier, if you're going to be doing problems in 2D, you can't be working with the local coordinate system. So you have to basically we want to basically transform this matrix to be compliant with the stationary coordinate system, okay? So essentially, we're going to apply our transformation matrix on both sides of this equation, okay? So we want to be able to perform calculations so that instead of F1 hat, F2 hat, D1 hat, D2 hat, we have these in terms of the stationary coordinates instead. Okay. Good. Okay, so before we do that, we actually need to expand this matrix a bit, okay? Because remember, everything we've been doing up until this point has just been 1D problems, right? So essentially, we're only really looking at deformations in the x direction, right? And so, this matrix here is not, this is how we've defined it up until this point. But if you want to do it in terms of the coordinate systems, in fact, all of these are all in the x direction. So this is F1 x hat, F2 x hat, D1 x hat, D2 x hat, okay? And so first thing we're going to need to do before we actually apply our transformation matrix is to actually expand this to include the y direction, even if there's not going to be any deformation in that local y direction. Right? Because our transformation matrix here, it doesn't work without the y direction. So we need to be able to do that. Okay. Okay. So the way we're going to do that is we're basically going to add rows and columns of zeros, essentially. Okay. Okay. All right. So that's going to expand our matrix actually quite a bit. So instead of our humble 2x2 matrix, we're going to have this, I would say, a little bit more cumbersome 4x4 matrix. Okay. All right, so we have F1 x hat, F2 x hat, or excuse me, F1 y hat. Okay, so F1 x hat, F1 y hat. Okay, F2 x hat, F2 y hat. Okay. And so we're still going to have AE over L. Okay, so we're going to have our truss spring constant out in front. Okay. And then we're going to have our element stiffness matrix now, right? So remember, we're not going to have any deformation in the local y coordinate. We just need to include it in our calculations. And so we're going to basically fill in all the space with zeros. Okay? So remember 1, 0, minus 1, 0, 0, 0, 0, 0, minus 1, 0, 1, 0, 0, 0, 0, 0. Okay. And this is multiplied by the same analog as our force vector. So this is D1 x hat, D1 y hat, D2 x hat, D2 y hat. Okay. All right. So hopefully you can see that, this expanded system mathematically is exactly the same as our original system here. It's just we've kind of padded for that extra space to include the y direction. Okay. And remember, we're doing so just so that we can apply our transformation matrix. All right. Any questions on this so far?
How would you handle cases where you have kind of like a composite where they have different properties in the x and different properties in the y? That's
a great question. So in those situations, you're probably using a more complex finite element method. So direct stiffness method basically doesn't account for that. Although one way you can do that with element stiffness or with direct stiffness is that you basically break up the element into different elements kind of stacked on top of each other. Mm. So you have like one element here stacked on top of another element, then maybe this one has different properties than this one, and you kind of stack them on top of each other just like that.
Would that be an efficient way, or is there?
That would not be an efficient way. So there's definitely better ways to do it, but that would be kind of I would say kind of a crude way to account for that in situations like
Would
this.
that be the scope out of this course, outside of scope?
I mean, technically we could do it. In fact, I think one of the future homework problems I give you, not really composite material, but I do give you a material that tapers. And so basically you're gonna have different elements have different cross-sectional areas. So that's something we can definitely do. It's just, you know, yeah, there's limitations in terms of how much we can actually do with that. All right, question in the chat. Let's see. All right, question in the chat. So we get a 4x4 due to the 2 nodes, 2 directions per node. And so 3 nodes, we get a 6x6 and so on. Yes, that's correct. So yeah, so things are going to explode fairly quickly. So, you know, luckily, you know, we're for the most part in our direct stiffness, we're not going to look at elements that have more than 2 nodes. But eventually we are going to look at elements with more than 2 degrees of freedom per node. So you see once we get to frame elements, we're gonna consider the X and Y deformations on each node plus a rotational aspect as well. And so that's going to get you a 6x6 matrix just with 2 nodes. And so, yeah, it very quickly gets out of hand and very tedious for sure. And you can imagine what can happen in 3 dimensions too. So in 3D, yeah, it gets even more out of hand for sure. All right, any other questions on this? Okay, all right, so we don't have time to finish the proof, but I do want to kind of show you the next step, okay? Because essentially what we're going to do is we want to replace these 2 ends here with, you know, the corresponding stationary coordinates, okay? And so we're going to apply our transformation matrix, okay? The problem is this transformation matrix is only basically applied to 1 node at a time, okay? Okay, but you know, our element stiffness matrix here obviously has 2 nodes, okay? And so the way that we're going to do that is we're going to basically put the same transformation matrix twice in the same 4x4 matrix, okay? So for example, let me show you. So if we take this F vector here, right? So we have F1 x hat, F1 y hat, F2 x hat, F2 y hat, okay? Right. And so eventually, you know, we want to transform this into the same version without the hats. And so we have F1x, F1y, F2x, F2y, okay? Or the x and y directions on the rightmost vector are defined relative to the stationary coordinates, okay? All right, so, but to do that, you know, we need to perform our transformation matrix, okay? Right? But our transformation matrix is only 2 by 2, right? And so the way that we're going to do that is we're going to take advantage of the fact that, you know, F1x hat, F1y hat, F1x, F1y, those are both in kind of the top 2 rows here, okay? So we're going to apply one transformation matrix right here. Okay. So that's going to transform the coordinates for node 1. Okay. And then we're going to apply the exact same transformation matrix down here. Okay. So this is going to transform our node 2 coordinates. And so let's go ahead and plug in the values of our transformation matrix. So I'm going to use shorthand notation. And so instead of writing cosine of theta, sine theta, I'm just going to use C and S, okay? Okay. Or C here is cosine theta, S here is sine theta. Okay. So we have C, S minus S, C. Okay. Everywhere else, just like we typically do in our assembly, everywhere else that's not defined, we're going to add a 0 in there. Okay. Okay. So just for the sake of simplicity here, I'm going to call this big chunky matrix here. We'll call this big T. Okay. right? And so as you can imagine, we're going to apply big T. We're going to apply one big T on the left-hand side. We're going to apply another big T on the right-hand side, okay? So let's go ahead and plug that in. So we have big T, and let me underline it just to denote that it's a matrix, okay? Multiplied by, right? So if we have big T there, we're going to have things in the stationary coordinates now. So we have F1x, F1y, F2x, F2y, okay? Is equal to AE over L multiplied by our element stiffness matrix, 1, 0, minus 1, 0, 0, 0, 0, 0, minus 1, 0, 1, 0, 0, 0, 0, 0, okay? And we have the same thing that we're going to transform on the deformation. So we have big T multiplied by D1x, D1y, D2x, D2y. Okay. Okay. Oh, we're so close, but I feel like we just don't have enough time. And not because there's many more steps in the derivation. We're basically right there. It's just that the end product takes literally two minutes for me to write because there's so many sine and cosine terms. Right, so we'll do that next time. But the last step in this derivation here is to basically take this T matrix and move it over to the right hand side. Okay. And so the way we do that, because we're working with linear algebra systems here. And so the way that we're going to move that T matrix over is we're going to multiply, we're going to front multiply both sides by T inverse. Okay. Okay. And so in the end, what we get is F1x, F1y, F2x, F2y is equal to T big T inverse times AE over L times matrix 1, 0, minus 1, 0, 0, 0, 0, 0, minus 1, 0, 1, 0, 0, 0, 0, 0, multiplied by big T, multiplied by D1x, D1y, D2x, D2y. Okay. All right, so we've accomplished our goal. So everything here is in terms of the stationary coordinates now, okay? The only thing left to do, and I say that as if it's a simple thing, is we need to multiply all of these matrices together. But this combination right here, this combination of transformation matrix, element stiffness transformation, this is the element stiffness matrix that we're seeking here, okay? So this right here is the element stiffness matrix of a 2D truss in the stationary coordinates. Okay. All right, and so when we come back on Tuesday, we'll perform that matrix multiplication, or I'll just tell you what the answer is. But even just writing the solution takes a lot because there's a lot of sines and cosines there. Okay, so we'll write that. We'll do some examples, and then yeah, we'll finish up our Truss stuff next week. So thank you guys for coming today. I know it went over time a little bit today, so I apologize for that. Hope you guys have a good rest of your weekend, and I will see you guys on Tuesday. Yeah.
So pretty much correctly, but this is like just
Yes, the only thing, it doesn't look like you have the fixed support. So I mean, I see the force here, but you need to apply the duration of that condition. Otherwise, this system won't be solved. Otherwise, exactly.
Oh,
exactly.
So it's kind of for pretty much one pretty much similar.
Exactly.
Okay.
Yeah. So they're they're all 1D problems, and so yeah, you should be able to do them already. It does get tedious, to put it like, and that's not even the most tedious thing. It's gonna get even more tedious.
Yeah, I was like waiting for the thing, I'm looking at it, all the notes and it didn't show up.
Yeah. Part of my motivation in this part is to make you guys hate the hand calculation, so you're more motivated to learn the program your own kind of help.
Okay. All right, thank you.
Yep. How's it going? Can't wait for enrollment to be over.
They need to have a talk with some of the other professors who just be like, yeah, sure, we can join this actually.